kidney on Wednesday. Okay, that was our little respiratory guy. All right, so a lot of this was chapter 17, and the people tonight will see too is all problem based, really. How do we breathe, basically, and then how do we do those math problems? But this was a conceptual thing that you could memorize, but I would prefer not. So the idea of this is when you look at how these, remember, bronchioles, arterioles are controlling flow of blood or air. And so if you look at this, they sort of are different, the pulmonary arterioles, than both of the others, as far as how they're responding to gases. And again, it's sort of odd, but it's the exact opposite. So the way I explained it is the way I'll explain it again. Sort of how I figured out instead of memorizing it. I sort of, you'd like to think of jobs that different things do, right? You kind of got that idea. And so I have sort of the systemic arterioles here, okay, the bronchioles here, okay, because I sort of make it like the chart is. The bronchioles, again, are controlling airflow into the alveoli. Okay? Our bronchiole constrict and dilate, just like these arterioles constrict and dilate. In fact, they have some of the same receptors when you go back to it. Here, these are the systemic arterioles. These means they're through the body guiding or delivering oxygen and other things to the tissues. Okay? Now, what we're going to have in the middle here, we'll go ahead and show their first picture, is the pulmonary arterioles. Okay? In that case, we're talking about that we have all those billion or so alveoli, and the pulmonary arterioles are going past these as air is going to the lungs to try to pick up oxygen and deliver it to the body, right? We're delivering it through the pulmonary vein, right, going out. Pulmonary artery, you go to the lungs, and we're going to do the exchange to get oxygen. And this is what these pulmonary arterioles are doing. They're trying to pick up oxygen. So, you want to think, if you're trying to think of, instead of memorizing why it's opposite, see if this makes sense. If not, it doesn't. But for the systemic arterioles, again, we're talking gases, and, let's take the example of low O2, which, of course, all these is analogous to high CO2, right? We're kind of used to these arrows. But we'll just talk low O2, okay? And we'll talk low O2, and we'll talk low O2, okay? These are the ones in the middle of that chart, which are kind of shown there, the pulmonary arterioles. And so for these outer ones, physiology makes sense, okay? A lot of physiology is use your common sense, and your common sense will probably mean that's right, because it works, and we're here. So if you just think of it, okay, the systemic arterioles, okay, they're sort of being, functioning to help out the tissues here, and if you have low O2, what are the systemic arterioles going to do? Are they going to constrict or dilate? Dilate. Because their job is to move O2. Deliver oxygen to tissues that need it. So low O2, they're going to dilate because their job is delivery. That's how they get paid. Yeah, I'm thinking of paydays now. Their job is delivery. If this tissue needs O2, which it does, they'll dilate to deliver it. Okay? That makes sense, right? It makes sense that it's going to do that. Why would it constrict? It has the O2. You don't have enough, it dilates. We come over here. Okay, this particular alveoli, we have a lot, but this doesn't have very much O2 either. And the bronchioles say, okay, what are they going to do? Dilate to, because where is the O2? It's out here. Their job is to basically deliver O2 to the alveoli when it needs it, so we can get it into the body. If we don't have enough, they dilate, and it will then deliver O2, we'll raise that up. Again, bronchioles is to deliver their job, they get paid for delivery, to deliver O2 to the alveoli. And then, of course, that will get to the blood. Delivery. If you need it, they'll deliver it, which means they'll dilate. That makes sense. The difference. How the pulmonary arterioles are going to get paid is their job, and they get paid by how much oxygen they pick up. Okay? So their job is to pick up O2 from the lungs, and then of course they'll deliver it, to the heart and the body, right? I mean, right now we have all that deoxygenated blood, we do the CO2 exchange, but we've got to pick up oxygen. Okay? That is our job. That is what we get paid for. The more we pick up, the more we get paid. Okay? Because we're all trying to make a living here, right? The more we, in this case, if their job is pick up, the more we can pick up, the greater we get paid, and it's flowing through very quickly. Okay? We remember we have, billion of these, or whatever it was, 100 million, and we're having this pass through very quickly within a second. And it's got to make decisions on where to go. Okay? And so here we have this idea, well, this one has low O2, so this one where we have relative high O2. And so here's trying to make a choice. If you're thinking of it the way I'm sort of describing it, I'll go ahead and throw the other words up here. So here's sort of the example I have up here starting off. For whatever reason, okay, and we can talk about that if we need to, this alveoli has low O2, like I have over there. This has high O2. So, if you get paid for how much O2 you pick up, which one do you want to go to? Do you want to go to this one or this one? This one. So what are we going to do here? And here, dilate. And that's why it works opposite, okay? Because its job is not delivering, its job is pickup. It's going to basically match wherever the more oxygen is, it's going to dilate direct blood flow there to pick up the oxygen. Okay? We don't want to waste our time over here. Hey, maybe we'll get more oxygen in there later with the bronchioles, but hey, right now it's like, let's pass through. We pick up as much oxygen as we can. And so that's why it sort of works the opposite. Their job is not delivery, but pickup. So in this case, they're going to go where the oxygen is. They're going to, their picture's probably better, they're going to dilate here, but on these ones, which we've been doing, those dilated, these are going to constrict. Okay, it doesn't have as much oxygen as this one. Let's direct the blood to these to pick up the oxygen and get to the body.
Are you saying they always are in pairs of that, or no?
No, this is in, yeah, I mean, this is in branching into millions. Yeah. Okay, so it's like a whole network here because we have 100 million. And basically what this is going to mean for us overall usually is we have regions, do you think every one of our alveoli and our entire lungs are working right now just to sort of sit there? Would that make sense? Okay, are we filling up our entire lungs right now just to do some simple breathing? No. We actually shut off a lot of parts of our lungs because right now we don't need it all. Okay, if you start moving around, talking kidneys and respiratory like this, okay, I'm going to be oxygenating more of my alveoli and we can pick up more of that. If we're running away from a bear, boom, we're going to oxygenate basically as much, almost all of our lungs, and then do it. So basically, it's not really pairs, it's really sort of going to regions of the lung. Regions of the lung, we're not going to actually oxygenate because we're not needing it for a normal thing. That's why those are sort of low, and then others we are. So really not even paired together, they're sort of in regions here.
So that alveoli, is that just like the surface area of where it's picking that up?
Well, what are you asking?
Because I'm trying to understand, okay, I understand the concept of how it's picking everything up, but I'm trying to understand, how it actually looks like. It's like a,
It's in the lungs, it looks like a sac of
yeah, it looks like that, right? But there's a lot of those, right? And each one's doing the same thing, but a lot of them at the same time.
Yeah. And so, it's looking at this, right? You have all these, and you have this capillary bed and pulmonary around it. So the thing is up here, the ones which don't have as much oxygen, these little balls that don't have as much oxygen, we're going to be sort of constricting blood flow there and maximizing blood flow, let's say over here.
Oh,
Okay, if these ones have more. So the alveoli, again, they're air-filled sacs, but they're also, instead of just showing like this, they're literally surrounded by this capillary bed for exchange because this is a sphere, not like a two-dimensional.
Yeah, that makes a lot more sense.
Yeah, it's hard. We go from 3 to 2-dimensional. Again, videos sort of help on this as well. So any YouTube things you get might actually help. But did that sort of make a little sense? I mean, you can always memorize that if you want. But it's nice if it makes some sense to you. And again, just one more thing, and I'll kind of do it. The job thing is how I like to remember it. I mean, this is, again, how I remember things because it makes sense. If you want to know the official terminology to impress your friends, it basically says what's up here. Ventilation, which is how much oxygen comes in. Do they actually keep it up there? Okay. Okay, well, let's just keep that up there. I mean, it says it. Ventilation is going to match perfusion. Ventilation is how much air we get in. Perfusion is how much air, oxygen gets to the blood, perfuses into the blood. It's going to match. That's the key. So that, if we kind of go to this one, that the low oxygen, we basically constrict it, so not as much is going to perfuse in the blood. This had high oxygen, ventilation was high, then we basically expanded so perfusion is high. We're literally matching the vessels, because the vessels are basically deciding on what's going to get to the blood, what's going to perfuse through the blood. So instead of doing the job routine, okay, you might have to kind of look at this. It's the idea of matching ventilation and perfusion. We're going to match how much oxygen gets in to how much gets to the blood. A lot gets in, a lot gets to the blood. Not that much gets in, not that much gets to the blood. So that's the official terms for your reference. Are we good? Chapter 18. Gas exchange is the harder of the two chapters.
Harder of two, you mean 17.
It's harder. It's of the two respiratory. This one's harder than this last one, and 20 would be harder than 19. But if you really on this chapter, I know I was in a theme here. Okay, I was trying to calm myself down. Okay, so I'm like, okay, let's just concentrate on your breathing, Mike. Concentrate on your breathing. Okay. Everybody always says, relax, Mike. Relax, Mike. Relax. And I'm like, okay, I'm trying. Okay. But the key with this chapter is make sure you really, for a lot of these now, we have the handouts and everything, or maybe you print out the PowerPoints. You really want some separate paper, because sometimes the way I explain it on the board and draw it is a little, is another way to look at it. It might even be simpler. So, have some paper here for these chapters. That helps. So, we're doing gas exchange. Oxygen and CO2, how we transport these gases. And this is a reminder. And we're going to look at a couple numbers, but we're not going to memorize them. We keep talking about how do we transport gases throughout the body. First day of class, remember when I was like running around saying concentration gradients, and you're like looking to see who else's class you can get into, but it was full. Well, again, you're starting to see that more and more, right? It's concentration gradients, it's pressure gradients, it's electrical gradients. It's all about gradients, and that's how gas is going to flow. So it's going to flow from here to here because higher concentration of oxygen in the alveoli than the arterial blood. It flows to the tissue, same way, higher versus that, etc. for CO2. So it is going to be that. Now, a lot of words here. Don't go freaking out on me here. But because really, I'm going to have the bottom line of what I want from this. But what we've got to deal with is, we've been talking about oxygen and CO2 in the air and the partial pressure of it. Well, once it goes into the blood, a liquid, we have to look at how soluble the actual gas is. How easy is it for it to dissolve into the blood? Because that's pretty important, because we've got to transport it. And so overall, again, that's why it's a little more physics than I want. I'm going to want a bottom line is. But if you look at this, here's oxygen at a given concentration, okay? Here's CO2 at that same concentration. This is the same partial pressure of the gases out here, in the air. Now, look at when it gets to the blood. Which one is more soluble? CO2. Okay? Because you see more of these molecules are dissolving in. It dissolves better. Okay? Oxygen, not so good. And when you look at it overall, this is what I want. Carbon dioxide, 20 times more soluble. So we're not going to do all this math up here, that's looking up here. We're going to basically show this, that it's carbon dioxide 20 times more soluble than oxygen. So that when these gases are going to be going around the bloodstream, as we're going to talk about, CO2, a lot of it can actually just be dissolved. Okay, like you dissolve salt, right? It would dissolve. Oxygen, not so much. What do we need? Hemoglobin. We're going to need a carrier for oxygen. And we're going to see hemoglobin is the man, or the woman. Okay? We're going to have it do a multifunctional thing. One thing it's going to do is, since oxygen doesn't dissolve, it's going to carry it. And we'll see a hemoglobin molecule can carry up to 4 molecules of oxygen at a time. And that's why our red blood cells don't even have a nucleus, organelles. They're like, I'm going to have hemoglobin and all the enzymes that I need. That's my job totally, okay? Because it's pretty important. Again, we need oxygen, and it's not dissolving very well. So that's out of all that sort of words, that's really the only thing I want us to get. Yes, ma'am?
Hemoglobin's a protein, or what is it?
Hemoglobin's a protein. It's going to be 4 protein chains coming together. It's really a cool protein, okay? This chapter is going to sort of show you that. I'm not totally into the respiratory system compared to the kidney, but I'm sort of getting hot on hemoglobin, and you'll see why, yeah.
So the hemoglobin, does it make it, the oxygen about as effective as the CO, the carbon dioxide? I mean, because you're saying it's 20 times more.
Yeah, it makes up, it basically allows, I mean, again, it's hard to say, but it makes it so we don't have a problem, okay? That we're able to deliver as much oxygen as we are to get rid of the CO2. We're able to do the system efficiently, which of course makes sense because we're here. But we're going to show you hemoglobin's pretty interesting how it does it. Okay, so let's look at this. We're not memorizing all the numbers, although you're going to see that we are going to sort of just know them as we get through the chapter. So, you know, we keep saying, or I keep saying, it's going to be diffusion from high concentration to low concentration. So let's just look at this. Again, you'll see which ones you end up needing to know. But the idea is the partial pressure of oxygen in the lungs, okay, is about 100 millimeters of mercury. The venous blood, it's about 40. So which way is it going to flow? Okay, until we reach equilibrium. That's why it's going to flow, when we just did this, the oxygen from the alveoli into the arterial blood. Okay, and again, then we'll talk about hemoglobin. Okay, we do the cardiovascular system. We get to the tissues, and the tissues have 40 millimeters of mercury of oxygen or less if we're more active, right? We start using it up. So why is it going to flow there? High to low. It's not like, hey, we need it, please flow there. It's literally concentration gradients. Okay, 100 versus 40, boom. Okay, and then of course, we equilibrate and we go out again and we do it again. If you look at CO2, same type of idea. We're not memorizing the numbers, but the idea is the concentration of CO2 building up in the tissues is 46 or more if you're really active, and on the arterial blood it's 40, okay? High to low, okay, and high to low. That's how we're getting rid of the CO2. So we're just showing you, instead of just saying concentration gradients, actually some of the actual numbers here so that correlates, so you know I'm not making it up. So you're not memorizing all these numbers, but you're going to see which ones we end up knowing. I just really want to show you sort of a real life situation versus just saying, hey, high to low. So, but it is high to low.
I don't see when you're pointing to the bottom how it's going from high to low. It's going to 46 to 46. Why is that?
No, because so the way they draw it, it's saying that the incoming blood, it's only at 40, and the tissues are 46. So it's basically going to go, 46 is higher than 40, right? So it's going to go into the blood, and now it's equilibrated at 46.
Oh, okay.
So the pictures aren't perfect on that, but that's sort of how it's supposed to do it. So you got to have to see it coming in versus this. But then it's confusing, right? I see that.
Like it's going the same.
Yeah, it looks like it's not even changing, but yeah, so you're sort of going, it's coming in at 40, this is 46, it flows into that 40 until everything's 46. But, good point, because the picture's a little off. All right, that's all that says. Okay, this isn't in your handout, and I want us to know this. So, it's in your PowerPoint, it's in the book, because all of you read the book. But, what I want us to know, and I'm going to kind of go through this, and it's not exactly the memorization is, well, you have these terms up here. So hypoxia are when cells aren't receiving enough oxygen. Hypercapnia, which we'll see a lot in the chapter, we talked about CO2 sort of causing some bad problems. If you start having too much CO2, the condition is hypercapnia, and we'll see the result. So a couple of terminologies. But when you look at hypoxias, hypoxic conditions, there are 4 basic types. And the reason I like this is we can actually follow it from the beginning to the end of what might cause the cells not to receive enough oxygen. So we get rid of this. And I sort of draw, I draw, let's see, here's our, this will be sort of, and we'll use this later too, this represents our alveoli. I'll just make a big one. Okay, there. This is going to be sort of, our blood, so these will be our red blood cells, RBCs, okay, and this is the plasma of the blood. So here's our blood vessels. Okay, here's our lungs, here's our blood vessels containing our cells. What's in the cells, by the way, will be hemoglobin. A lot of times you're going to see, you know, we abbreviate hemoglobin HB, and that's what I kind of did here. So that's that. Over here we got our heart that we're going to deliver that blood to, and that's going to go out through the aorta to the cells. Cells and tissues. Okay, we'll make a big cell. And that's sort of the pathway, right? We're picking up air from the lungs. It's going to go in the blood, including the hemoglobin. The cardiovascular system is going to now transport that oxygenated blood to the tissues. Hypoxia is these cells and tissues are not getting enough oxygen. But why? And we can follow this overall, sort of showing, and I kind of use this. The reason I like this is we start at the beginning and we go toward the end. If you basically are not getting enough oxygen, you know, into the arterial system, because this is where it's going. So we're not getting enough oxygen here, right at this first step. It's called hypoxic hypoxia. Okay? You don't have to memorize these per se, but you can kind of see what might actually happen. Okay? If you don't have enough oxygen in here, okay, you know, you're at high elevation, so you just don't have enough. You're not going to have enough in the blood. If you have sort of fluid buildup or some fibrous tissue buildup, something that doesn't allow that nice, easy exchange, it could be several different things. But the bottom line is, if you have low O2, just right at this first phase, right from the blood or the alveoli to the blood, that's called hypoxic hypoxia. Again, it says low arterial PO2. Okay, that's one. Now, let's say that's not the problem. The second one, you know, we mentioned anemia is when you don't have enough functional hemoglobin. Hemoglobin is going to be the person who transports. So let's say you get it in. There's no problem. We have plenty of oxygen in the lungs. It diffuses into this area fine. But the hemoglobin, either we don't have enough red blood cells or we have sickle cell. The hemoglobin doesn't work. Either way, it's the same thing. That's anemia. So what are we going to call this?
Anemic hypoxia.
And that should make sense. So we're all going to be following. That's why I like this sort of idea. You know, it's not really it's a chart, but it's showing you sort of 4 different locations along this pathway how something might go wrong and basically make it so these cells are sort of choking, not enough oxygen. The first one, hypoxic hypoxia, we're not getting enough into the blood. The second one, anemic, it gets to the blood, but we don't have its carrier. Not enough cells, not enough functional hemoglobin. Either way, that's anemia, that's anemic hypoxia. Okay, let's say that's all good. We make it here. But let's say our cardiovascular system is compromised. You know, our heart's failing, low cardiac output, you know, we have blockages. In that case, we're not going to deliver the oxygen to the cells. Okay? Hey, we got it in, the hemoglobin's got it, but it's not going to efficiently pump it out to the cells. And we're going to call that ischemic hypoxia. Okay? So if you got a problem here, and that guy looks sad, where we're just not delivering enough, our cardiac output, our heart's not working well enough, and the cells are not becoming oxygenated, that's ischemic hypoxia.
Is that oxygen with the arrow though?
Is what? This
Cardiac
was saying
output.
something like,
Okay.
you know, your cardiac output, because we all know CO for cardiac output is inadequate. Or it could be some other blockage, something affecting this delivery to the tissues. But usually, as we kind of find from our whole system, it's something where your cardiovascular system is not efficient. Usually the heart is sort of, you know, failing. Last one. All this is fine. Boom, oxygen gets in here. Hemoglobin says, no problem, deliver to the heart. Heart says, hey, I'm good. But we somehow poison the sort of the cells, basically, where the oxygen, it kind of says it can't be used. Okay? The oxygen has to get into the cell and get to the mitochondria and be used, etc. We're not going to metabolism, but it's got to function within the cell. And if you poison this so it no longer works, it's called histoxic, which should make sense. You can see this toxic here. Basically, like cyanide's one example of what it does. Cyanide, basically, you deliver oxygen, but you make it where the oxygen can't be used by the cells. And the cells then hypoxic and die. So this is called, if you have sort of the poison, histoxic, the keyword sort of is toxic hypoxia. So again, know this. It's not going to be an essay. I'm not going to have you draw all this out or anything like that, but it'll be some multiple choice questions. So realize sort of what they are. I just like to do it this way because, again, you see, I mean, you know me by now. I sort of like, I don't like memorizing a chart. I like it so there's sort of a flow of thing. You can see what can go wrong along the way, at least briefly.
For the first one, can you explain why high altitude would give you low pressure in your lungs?
Because, well, the whole key is, in fact, we kind of did this before. I mean, you need, at low altitude, you have a higher percentage partial pressure of oxygen.
Because it's lower outside and it's going from high to low?
Let's say, I'm just saying, like at normal altitude, okay, if you go back and you actually do even Dalton's law, you have a partial pressure of 154 or something, and that's enough to fully oxygenate. Higher pressure, like you're going to Everest, there's simply less oxygen there. There's less, overall. Less oxygen means there's not as much oxygen going in. So that, but if you have, let's say you have some sort of blockage, that's another way you might not get enough oxygen in the lungs, and also then cause that too. So there's a lot of different ways, basically, but that's for altitude. You just don't have that much air out there, so not much oxygen. Okay, let's talk hemoglobin. Now, again, very wordy things, and this slide won't be perfect, but I want to mention a couple things about hemoglobin. And then, again, we're going to do oxygen transport. And we'll see how far we get with this other thing. So, as we sort of say up there, and it's kind of over here, we're going to talk about it, just to kind of orient on this chart too. Here's the oxygen, kind of as I had it. I'm going to redraw that. Coming from the lungs, it's going into the arterial blood. Here are the red blood cells with hemoglobin. Cardiovascular, this is kind of what I have up there, drawn like that. And as it sort of says here, the idea is since oxygen is not very soluble, not much of it's going to be delivered, just dissolved in the plasma. Most of it's going to enter and be bound by hemoglobin to be transported. Okay? That sort of makes sense. The second slide is, if you look at hemoglobin, 4 chains. So it is a protein. It has what we call quaternary structure way back when, because basically it has 4, it doesn't have to be 4, but it's got multiple subunits coming together. And in the adults, and we'll say something different later, 2 alpha, 2 beta. Each one has this heme group capable of binding a molecule of oxygen. Okay, that's the basic structure of hemoglobin. Okay, 4 chains, 2 alpha, 2 beta, each one capable of binding oxygen. So again, one hemoglobin molecule can bind 4 molecules of oxygen. But it also binds other things that we'll actually see will be important. And it also will bind, we can kind of put it here, it actually binds CO2. It's going to help us transport carbon dioxide. It binds hydrogen ion. And hydrogen ion means what to us?
Acid.
Acid, pH. So it's going to act kind of as a buffer. Pretty nice of it. Okay, this molecule, you're going to be like, whoa, this guy's pretty cool. Not the kidney, but pretty cool. Okay, it does that. It also binds CO. What is CO? Uh-oh. So you didn't like my last test. Went to the garage. No, but then you changed your mind. You said, I have 2 more tests left. So carbon monoxide, the reason it's so sort of deadly is, you'll see these other things bind to these other sites. Carbon monoxide binds to the oxygen binding site. It binds again. I just put this slide up, so again, it's not in your handout. I wanted a little more detail, but it binds 230 times the level of oxygen. It outcompetes oxygen. That means it's almost irreversible binding. Boom, it stays in. Okay, and obviously that's not a good day. We'll actually show something of it. So. Okay, so I have to erase the pot. I don't even want the term there right now. But basically, that's what carbon dioxide is doing. Okay, that's why it's so deadly. It prevents, it's sort of interfering with oxygen binding, and obviously then you're going to become hypoxic. So, the next thing, and this is why I want you to sort of write this down separately. I'm going to list 6 steps to oxygen transport, and it's going to be as simple as that. Then comes El Diablo, but we'll wait on that. That's what Stu called it, and I'll talk about it as it goes. Again, Stu Matz, who I keep mentioning, whoever I was going to try to take his class because the tests are easier, but he's so cool. You'll love Stu. Okay, recommend Stu beyond a doubt. But again, I took his class, and when we went to this day, he's like called this chart El Diablo because he's been teaching it like 10 years. He said basically it's one of those things that often confuses students, and he figured out a couple tricks, and I figured out a couple tricks. Try to make it easier to comprehend, and that's coming up. But this will be easy. Okay, so let me redraw this just to kind of use it here, and I'm going to list the 6 steps of oxygen transport. So we have the alveoli like they have there, and we're going to have our red blood cell, okay, with hemoglobin, okay, and then we're going to deliver it to the tissues. So you see down here, the red blood cell made it all the way through the cardiovascular system. Here's our heart, kind of a little heart, and here's our red blood cell delivering oxygen to the tissues. Okay, and here's hemoglobin. But we'll fill that in. So, 6 steps of oxygen transport. And so this is O2 transport, the easy way. 2, 3, 4, 5, 6. So, first step is we had numbers up before. We have a lot of oxygen in the lungs, not as much in the blood that's coming in, and so oxygen is going to do what? More here than here. Where's it going to go?
Move down its concentration.
Down its concentration into the plasma. Don't think it's automatically going. These cells are not fused. Remember, we've got plasma around these cells. That's the first step, which is this, and that's what I'll write. So step number 1, actually it's sort of interesting, it's sort of the same here. Step number 1 is oxygen is going to diffuse from the alveoli into the plasma. Okay, and that's what I'm going to write. So that's step 1. Step 1, oxygen diffuses down its concentration gradient from the, again I could put lungs or alveoli, I guess I'll put alveoli, into the plasma. Diffuses from the alveoli to the plasma. And overall, again, a couple percent or so might be actually transported that way. But we're not done yet. So it basically, step 1, again shown here, is diffusion from high to low until it reaches equilibrium overall. But what's going to be the next step, you think?
It goes into the
Attaching to the hemoglobin?
Not yet. We've got to get it in there first.
Transport or
diffuse.
It's going to diffuse from high to low. Remember, gases freely diffuse across membranes, high to low. So high to low here, now it's going to diffuse from the plasma into the red blood cell. Okay? This is why you sort of, it's not hemoglobin, you can't get, hemoglobin's inside the red blood cell, oxygen's got to diffuse there first. So step 2 is that. Okay, the key word, of course, is diffusion. O2 diffuses from the plasma into the RBC. Until, again, if we did nothing else, we're just making, and diffusion only works until you come to an equilibrium, right? So we would come to all these would be even. But right now, this was higher, it diffuses out, okay? We have the concentration difference here, it diffuses in. And now, if we did nothing else, it would stop. Once we reach equilibrium, where we have the same concentrations here, nothing else would happen. We don't like that. That wouldn't get it very much, right? Because we already said oxygen doesn't dissolve very much, so we wouldn't really get much out. Step 3 is sort of the one that we already know is going to happen. Once oxygen gets in, it's going to bind with hemoglobin very efficiently. And of course, as it happens there, that means it's converted to this oxygen hemoglobin, and we can basically continue on. So let me just put 3 though. Okay, so step 1 was that. Step 2 was oxygen diffusing from the plasma into the red blood cell. Step 3 is sort of, I'll just draw it as I have it there, is it binding to hemoglobin? So step 3 is oxygen binds to hemoglobin. Now, what I want to say, and so again, I have that. That's step 3. We're going to call these first steps the loading phase, and you'll see why. This is where we're loading up with oxygen. Okay, at the level up here of coming from the lungs into the blood. So we have 3 steps. We have this idea of it diffusing from the lungs, from the alveoli into the plasma, and from the plasma into the red blood cell, and then starting to bind with hemoglobin. Now, I want you to think about this third one. Again, thinking about, because this will help us as we go, concentration gradients and diffusion. If we can kind of do it up here, it's a little messier. If we basically have, let's say we had 30 molecules of oxygen, okay, and we had 0 there. It's going to diffuse from high to low, but not all of it, right? It would be about half. So now you have 15 and 15 molecules of oxygen. Same thing here. It will diffuse in until it's basically about the same too. So if we did nothing else, we can only come to some sort of equilibrium. Let's say 10 and 10 and 10. But what if we take this free oxygen that made it in and bind it up with hemoglobin? Okay? What do we establish here now? Now we have 0 or 2 free. Now we have 10 and 2. What if we reestablish? A gradient. And now more oxygen will go in. If more of this oxygen comes in, what do we reestablish here? A gradient. And so this is the idea of exploiting diffusion. The idea is we have to obey the laws of physics, diffusion. But diffusion only allows us to get halfway. We are not satisfied with that. So here's our first exploitation. We have this idea, this is diffusion, this is diffusion. If we did nothing else, hey, we wouldn't get much out. But if we take this free oxygen, tie it up, we reestablish this gradient, more comes in. Now we reestablish this, and therefore more goes this way. So we are maximizing diffusion by doing this process. Step number 3, in effect, drives step number 1 and 2. Okay? Basically, oxygen binding to hemoglobin, and of course, that's how it's going to be most efficient. Basically, doing that, we're allowing this and this to occur more and more. This is simply diffusion, but we're maximizing it by taking this free oxygen to keep reestablishing these gradients. It's still all about concentration gradients, but we're exploiting it. And when we do carbon dioxide, you won't believe how much we exploit it. This is just baby exploitation.
Sorry, just trying to get a whole picture. I know that the red blood cells are what's flowing in the body, but why does it need to bind to hemoglobin? Like, why is it so important that that's in there with it?
Hemoglobin?
Yeah.
Because O2 doesn't dissolve very well. And that's why 98% is actually bound to this hemoglobin molecule. If you don't have hemoglobin, so little oxygen dissolves, you wouldn't be able to effectively deliver.
Do you mean like diffuses into the cell, or do you mean dissolves into what?
Dissolves into the blood. Blood is a fluid, right? And so in a kind of that very beginning slides, basically gases are out here. When gases are going into a fluid, a lot of it just doesn't dissolve. It has to be soluble in the fluid. So literally, it simply won't dissolve in. It won't be able to transport it. Okay? It needs to, just like salt has to dissolve in a liquid, oxygen has to dissolve, and it's not very soluble.
So it'll go into the cell, but it would just be...
It won't go into the cell. We're talking, right now we're talking here to here, okay? It basically won't, not much, since it's not soluble, not much of it's going to end up dissolving. You're not going to get it in. Just to go back just a second, just to try to clarify that when you come to the figure I didn't...
So hemoglobin is just a vesicle so that it's able to take its next step to go, right?
I don't like the way you sort of dissed hemoglobin. Yeah, it's just the next step. No, it's the major guy today. It's the star. Okay, right now it's the only way we're going to be able to do it. If you look at this is what we're saying. Okay, remember this is concentration of the gases here. But if we don't have hemoglobin and we're trying to carry it, only this much oxygen is going to get in because it just doesn't dissolve. So without a hemoglobin versus CO2, even though we've got all this oxygen, this is the partial pressure in the air, only this number is actually going to be able to dissolve. The others can't dissolve. It literally won't get into the body because it doesn't dissolve. So you're not going to get much oxygen in the body. And again, less than 2% really of what we need will actually be just soluble in there. But hemoglobin will suck up the rest. And that's why we need hemoglobin just to carry on the next just to carry on the next step. Does this help at all? I don't like these figures that much. But the idea is, just like anything dissolving, if you don't have, if for some reason, your salt can't dissolve very well, you're not going to have very salty or sugar. In this case, oxygen simply doesn't dissolve in our blood. So all the stuff from the lungs, basically only a few molecules would actually be able to dissolve and then be transported. The rest of it would just stay out in the lungs. We couldn't get it in. We need hemoglobin to sort of suck it up because it will carry it. And again, not only does it carry it, of course, it allows us to get more and more out. So, yeah.
That's what I was going to ask about the free O2. Can you explain again the process as to why it drives steps 1 and 2?
Yeah. So let's go back to that. Again, if you just forget hemoglobin right now, it's not there. Okay? And we talk diffusion. We go high to low until it becomes equal. So again, even if we just put over here, if we have, again, here's our alveoli, and then here's our red blood cell. And the idea of this is, again, if let's say we just had 100 here and nothing here, it's going to diffuse out and then diffuse out till we're equal. So we have 33, 33, and 33. Okay? And that will stop, right? Diffusion can't go if there's no concentration gradient. But if we take some of that 33, okay, that's free oxygen, that's what the concentration is based on, free oxygen. If we take 20 of those, okay, 20 O2s, and bind with hemoglobin, that doesn't count anymore. Okay, we hid the oxygen, it's bound to hemoglobin. So now we only have 13. Okay, now what do we have here? Concentration gradient. More of that goes in. So we have, 20 and 20. Now what do we reestablish here? Concentration gradient. More of that flows out. So by taking away free oxygen, we're driving these processes. We keep creating concentration gradients because if we get rid of it, we have this concentration gradient. It comes in, we have that concentration gradient. Okay? So don't go crazy on it totally on this, but it's just the idea is sort of, we're only doing diffusion here, but besides being the fact that's the only way we're going to be able to carry this, most of it, we're also making sure we maximize the loading up of oxygen from the lungs. Okay? Without this, very little is coming in. With this, we're able to get, well, all we need, but a lot is going to come in. So again, if you don't totally get the idea of how this drives it, don't worry about that too much. Okay, it's not the most important thing. But you do want to understand basically this loading phase overall. We're diffusing, binding with hemoglobin. So if this driving process drives you crazy, just sort of blink your eyes and forget about it, and just get, because again, I'll tell you what, the stuff to really emphasize that'll be hard, but that's just the way it is, and I'm sort of, I'm into it, but it's not some weird essay question. I really want you to get just the first 3 steps, and they're that simple. Oxygen diffuses into the plasma, it diffuses in the red blood cell, binds with hemoglobin. That's how we're loading up with oxygen. That's the real critical thing. Yes, ma'am.
For the third step, can we just put that when the O2 binding to hemoglobin equals like exploiting the concentration gradient?
And doing what?
Can we just put on that step that's where it's exploiting the concentration gradient, or you were saying?
Sure.
Yeah.
Yeah. Again, it's not going to be an essay, by the way, but yeah. Okay? Everyone's good on loading. Unloading, the opposite. And so, again, don't freak out on this, because we're going to take a minute and get to the hard stuff. Because the way I do this can sort of, again, people are like, twist their mind out. But, we sort of get this idea, so we're on the tissues here. We want to have that oxygen get in. Now, some people are like, okay, hemoglobin's going to let it go, and then it's diffusing out and diffusing out. To be honest, that's it's going to work sort of the other way around, okay? And so I'm going to draw it this way, but don't freak out. The idea will be the following, and then we'll kind of put it. The oxygen out here in the plasma, okay, because the red blood cells are not connected, right? We have plasma, okay? It's higher than it is inside the cells. So what's going to happen? This oxygen out here in the plasma is going to diffuse in, okay? Does everyone see that? Even without a red blood cell, that would happen. If this is higher than this, it's going to diffuse in. Now before, the amount of oxygen out and the amount of oxygen in, I hate the way they draw that, we were in equilibrium, right? We just established that. If we take some of this oxygen out, what do we reestablish here? Concentration gradient. More oxygen goes out. When you just think about the law of mass action, I mean, I like to draw double arrows. If this was a balance here, and we're getting rid of that oxygen, what's that going to drive? Okay, you put a hole in this side of the balloon, right? You're getting rid of a product. That's driving hemoglobin letting more go, because everything was in equilibrium. So what I'm going to draw up here, and then you could sort of forget about it, kind of, because I know it's confusing, is that step 4 is going to be diffusion of this oxygen that's out here in. Step 5, diffusion of the oxygen that's just free here out. And then hemoglobin is sort of unloading it to balance. So it's 4, 5, and 6 instead of like that. Because hemoglobin doesn't know, like, hey, it's time to let go. Everything's chemistry. The only way it's going to do it is sort of this idea. If we drew it this way, which I'd rather draw it, H2 plus hemoglobin makes this oxyhemoglobin guy as a reversible reaction, which is what it is. It binds it, lets it go. Okay? If you decrease oxygen by allowing it to go out, which way is this going to go? Which is basically hemoglobin letting go of the oxygen. So I don't like the way they draw it, but that's sort of the idea. So let me just write this. 4, 5, 6. So step 4, this is the tissues. Okay, we have oxygen out here. We have hemoglobin bound to oxygen. I'll draw it the way they do it. So this is going to be step 4. Okay, this is the oxygen that's in here out. It's going to be step 5. And then actually the hemoglobin letting go of the oxygen, step 6. So step 4, we have oxygen diffuses. Now we're at the level of the tissue. This, by the way, is the unloading phase. We're unloading the oxygen to the tissues, at least some of it. So oxygen diffuses there from that plasma into the tissues. Because it's higher in the plasma than the tissues.
I thought the free oxygen in the plasma was a very low percentage of what is overall getting transported.
True, but it's higher than what's in the cells.
Okay.
That's sort of the key.
Because now they're high carbon dioxide and they lost
Yeah,
their oxygen.
and they have, and so, you know, we say that, but when the actual numbers in place, which was in the other one, it was lower than or sorry, higher than this. Okay, it was like, whatever it was actually up to 100, you know, of it as far as pressure goes compared to 46. So the amount is very small out of the whole thing we're transporting, but the key is it's more here than it is here, okay? And therefore, if it's more here than here, it's going to diffuse. So oxygen diffuses from the plasma to the tissues, okay? Like with being step 4 here. Again, I don't like the way they draw it. Okay, the oxygen out here and here, we're in equilibrium like before, but now, boom. We put it in here. That means more of this oxygen can diffuse out. Okay? We put it in, now we have less here, more diffuses out. Don't even look at that stupid arrow. Because, again, you know, this is like totally confusing. This is not like fused to the cell. It's going, because there's plasma here. It's going from the red blood cell to the plasma. O2 diffuses from the red blood cell, RBC, into the plasma. And again, so we're doing this, because this was higher than this. Now we've reestablished this gradient. They were at equilibrium. We took some of this out. That means this goes here, and that's going to drive more unloading. So people like to go 4, 5, 6. I like to go 4, 5, 6. But don't freak out if that just pushed your mind. But that's sort of reality here. It's wrong to say, hemoglobin lets go of the oxygen and flows out, because that's not the driving process. This is the first driving, higher to lower, that drives this out, higher to lower, and that helps us, that drives the process of unloading. If it bothers you, don't worry about it, just write it down. Okay? So the final step is sort of HbO2 will be driven that way to basically release the oxygen. Okay? If it bothers your mind, don't worry about it, just write it down.
to release, what was the last one, to release O2?
To release O2. Because right now it had it bound, it's going to go that direction to actually release it. So it's going to end up getting there, okay? Whatever, if you want to look at it, this, that's fine. It's just in reality, it's sort of working that way as far as sort of just diffusion goes.
And that's the other step that's driving it all, is what you're saying is why it doesn't really matter how you look at it, whether it's 4, 5, or 6, because it just keeps doing
Yeah,
it over.
yeah, and that when it comes down to it again, it was almost like a pet peeve that I wanted to, because that's how it really works. It's not like we have a motor here and like go, pushing it out. It's literally only going because of chemistry, right? We made that lower, and that drives more, of a chemical reaction. But yeah, right. It's basically understanding unloading. Hemoglobin's carrying most of it. It's basically, basically unbinding it, it diffuses, right? So if that's all you want to get from it, that's fine. I got no problem. Because we got something coming up for the last half hour. So take 72 seconds to breathe, and we're gonna tackle El Diablo for the first time. Okay, drink if you have it.
In the last step, number 6, when we're releasing the O2, is that to the tissues, right?
Well,
Or just in general, because it already went through the tissue.
but we're gonna get more.
So a little bit of tissue.
But remember, it doesn't go to the tissues directly, right? It has to go to the plasma first.
Right.
That's why if you want to think of it O2, 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 that's fine. If that makes you, because that's what's happening, right? It's releasing it, it's then dissolving into it's going from here, now releasing it to the plasma, and then it dissolves from the plasma in this.
So the tissues get hit twice, so to speak.
It's all one, okay? It's just, you're not really being hit twice. It's just the process. If you want to think of the process of like this, that's fine. It's just, in reality, it's sort of working the opposite way. It doesn't matter. It's not really being hit twice. It's basically, ultimately, the hemoglobin is releasing its oxygen, it's going into the plasma and going into the tissue.
Oh,
Okay? You can think of it that way.
Okay.
That's really what's happening. It's just that. It's just a tweak. But I can't put it the wrong way. I'm sorry. I have to put it that way.
You gotta follow it.
Yeah, because that's what it really is, the concentration gradients. And so it isn't like you just decide, boom, I let go of it. It won't happen unless this happens and then that happens. Otherwise, we're at this equilibrium here, right? We said we were all the same up here, right? So if we didn't do anything else, that isn't going to let go of this, right? Because we had, this was the right amount. This was sort of at an equilibrium. The only way to have this release is to get rid of it. And that's going to be driven sort of by that. So. Okay, El Diablo. What El Diablo is the following. All those are the words we just said. It's called the hemoglobin saturation curve. Okay? And it basically is the idea, it's sort of a chemistry-looking curve, but we're a biology class. And so the key is to transform this, although if you're a chemistry person, you like this, we transform this into something that means something to us. And so we're going to do this in steps. Okay? The first step really is going to be sort of drawing this, and we figure out what sort of the shape of it, but also what these axes mean. Now, overall, what this is measuring, when we just say hemoglobin saturation with oxygen, okay, that's saying how saturated, how much oxygen is the hemoglobin holding. So, let's say if this hemoglobin or hemoglobin's holding 100%, if it's 100% saturated, it looks like this. It carries 4 molecules of oxygen. That would represent 100% saturated. That's the most oxygen it can carry. 100% saturated. The hemoglobin's 100% saturated with oxygen. Right? That's sort of the idea of saturated. If it looked like this, it'd be what? About 75% saturated, right? 3 out of 4. 75% saturated. If it looked like this, 50%. That's what we mean by saturation. How much oxygen is on the hemoglobin? So, let's draw this curve and then explain it. So, again, step by step. The first thing to be able to do to start to understand it is to draw it and see what these axes are. this axis is, the y-axis, is the percent saturation. Okay, like we just said. So what is the percent saturation of the oxygen on hemoglobin? It goes up to 100%, like we said before, and we can kind of go down 50, 25, and if it's at 0, that's really not a good day. Okay, that's why this is a chemistry curve. We'll talk about what's physiologically significant, but it's basically that's what this axis is. How saturated is the hemoglobin with the oxygen? Now, the key with this is, how saturated this will be is dependent upon how much oxygen is around it. If you have a lot of oxygen around it, it's going to help it become saturated. If you don't have that much, it will be less saturated. And so the bottom axis is, the x-axis, is the partial pressure of oxygen that is around it. So here we have partial pressure of oxygen. How much oxygen is sort of surrounding that hemoglobin? What is the, and again, sort of the pressure of it surrounding it? If this were the red blood cell, we said O2 is there, how much free O2 is there? And so, overall, that's the partial pressure of oxygen. And again, you go from 0, which would be pretty death, okay, into up to 100, in this case, we draw it up to 100 millimeters of mercury. But we also have, different ones, like we have 70, let's just put 40 there. And the idea of the curve, and then we're going to explain the curve. I just want to sort of get it here. The curve's going to have two sort of shapes here. Okay, and we're going to describe that. But before we actually, that's sort of the first part. But what you want to see is, partial pressure of oxygen from 0 to 100. If we put hemoglobin in a test tube, we can test it at 0 and 5 and 10. That doesn't mean anything to us. We have to say what concentrations really are physiologically significant. And these are the two big ones here. So when we say 100 millimeters of mercury, that's about the concentration it's being exposed to in the alveoli. Right, as we drew it up here. Remember, the alveoli had about 100 millimeters of mercury. That's what that hemoglobin is exposed to then. And if you look at that, hey, pretty good. Hemoglobin at that concentration is almost 100% saturated. Now, the other one that ends up being important will be 40. And that's the concentration of oxygen in a resting cell. Which, remember, means it's not highly metabolically active, but it's active. So this is going to be sort of something we're going to look at too. So, there's all these concentrations in between. Again, if you look at it, we'll create a shape like this. So, first thing, just be able to draw this. You have to know what these axes are. This is percent saturation of hemoglobin with oxygen, up to 100%. And this is how much oxygen is surrounding it. Okay, from 0 up to 100 pressure millimeters of mercury. That's the oxygen. The more oxygen, the more saturated it's going to be. But you see, it's not like a straight line. And so this is where Stu's sort of helping on this. He says, for this part, he says the following. To really understand this, you read it Hebrew style. Which means we're going to look at, for people that aren't reading Hebrew regularly, we're going to go from right to left. We're going to look at this and tell you what it does in the shape of this. And then we're going to look at this. You can see that the curve sort of has two basic places. The right phase sort of looks like a plateau. Kind of remember we did the plateau for the action potential. And then this is sort of a steep phase. So we're going to go there. And again, two bullet points. This is the next thing to do. Is tell us what's happening here and why is it that shape. What's happening here. And so number one, which is on the far right here, guess what we're going to call that? The loading phase. Okay, also called the plateau. And the two things we want to know about are the following. What's happening there and why is it a plateau? So what's happening there is this is where the hemoglobin is loading up with oxygen. Right? This is actually where it happens. So it's being exposed to that high concentration in the lungs, and it loads up almost 100%. Okay, that's why it's called the loading phase. Okay, that's the concentration. It's being exposed to the lungs. That's when it's sucking up, as we just described, and picks up the oxygen. So loading phase, basically, again, call that because, put a bullet point if you want. That's where it's picking up oxygen from the lungs or the alveoli, picking up O2 from the alveoli. Does that make sense? Okay, we just went through the steps. Okay, it's basically picking up oxygen in the alveoli, but the thing is, when it's doing that, this is actually the concentration. It's picking it up and becoming almost 100% saturated. It's pretty evolved, or whatever word you want to use, to do this very efficiently. So basically, you could be a couch potato, okay, and just watch football all day, and your hemoglobin's going to load up 100%. Okay, that's not going to be the problem. It's going to be the cardiovascular system getting it later. But right now, as far as our lungs go, boom, this hemoglobin will suck it up. Okay, so it's very efficient. The second question, the second bullet point for that one, and then we'll do the second phase, is, why is it a plateau? Or for us, in the sense of what is sort of the advantage of it being a plateau? Remember, this is working for us. If everything's cool, which it usually is, common sense, it's that way for a reason. So here's one way to look at why it's a plateau. Okay, let's say we aren't exposed to 100. Let's say we're at high altitude, or we're having some sort of temporary blockage, and we're at 70. Okay, do we want this a straight line where now only 50% of our hemoglobin is saturated? Wouldn't it be nice if it were almost fully saturated, even at those lower concentrations? That's the advantage of it being a plateau. And I'll kind of write it, sometimes it's wordy. Even at less than optimal conditions, let's say at 70, we're almost going to become fully saturated. That's how evolved this molecule is. So we're not really losing out that much at this level. Okay? Even if the lungs were not getting enough oxygen at that point, the hemoglobin itself, very efficient at becoming saturated, picking that baby up. So that's sort of the idea of why it's a plateau, at least in the sense of why, from our significance, it's good that it's a plateau. So picking up oxygen from the alveoli, and it's a plateau, sort of, it allows optimal loading. I'm always kind of wordy on this, but optimal loading of O2 I'm always bad at sort of that's right, in less than, I'm just going to make ideal conditions. Because I really want you to understand it more than being able to write it. Again, there's several other ways to say this. I've got to come up with a little more succinct way to say it. Okay? And again, stays pretty high, highly saturated, even at lower concentrations, whatever it works. Does everyone sort of get that idea then? Okay, it's again, you can see the loading thing. Okay, that's the concentration that's surrounded by in the alveoli. It loads up 100%. The reason it's advantageous to be a plateau instead of something like this, that if you have less than optimal oxygen, at the lungs basically, we still want it to be still fully saturated as much as possible, and we really don't lose much. Okay, so all the way throughout here. Again, this is one of those things too. You got to look at it a third time before you really fully get it. Okay, now we're reading this side, and you can see it up there. It's going to have the same two basic bullet points. Basically what's happening here and what's the advantage of it being steep, okay, being like this now. So we go through what's going to be the unloading phase. Okay, so it's called, again, the unloading phase because this is where it's letting go oxygen and delivering it to the tissues, to the cells. It's unloading. It's not going by the cells and staying 100% saturated and saying it's mine now. This is what you wanted to actually release oxygen to the cells, sort of as we did here. Okay? We wanted to release it and get it to the tissues and the cells. This is the unloading phase. And so the idea is, again, it's basically step number 2. You can sort of just writing that up there, but it's sort of the unloading because hemoglobin is unloading to the tissues. And let's look at this. At a resting cell, we're saying it's unloading. Is it going to release all its oxygen into a resting cell? No. Look at this. If you look at 40 and go up, it's basically now about 75% saturated. Okay? So we kind of put this, kind of get rid of that. Here's our oxygen. So it's about 75% saturated, okay? Which means, again, saturation's fine, but I'm thinking about, okay, how much did it release to the tissues about? About 25%. So if it's 75% saturated, about 25% of oxygen was released to the tissues. And I have that, of course, up there on the PowerPoint too. But does everyone sort of see that? We're not letting all of it go. It's not from 100 to 0 here. We're not letting all go. But for a resting cell, we're releasing only about a quarter, right? If you think of this as 100. If it's 75% saturated, sometimes I even write it, 25% released. That's being released to the tissues that need it. So it's not releasing all of it, because if you released all of it, and then you had to run away from that bear, and so your cells had less oxygen, you'd say, sorry, I gave it to that resting cell. So we have this idea of it being a reserve. That now the idea will be, when we are going to use it more and more, okay, as we go this direction, which is less oxygen, that means higher metabolism. Right? We're using up oxygen as we're going this way. So when we're using up oxygen, do we want it to deliver more oxygen? What do you think? Okay, if we don't have enough oxygen, do we want it just to release 25% or do we want to release more? More. And let's see if it does. Let's see we're at 30. It's at 50% saturated. How much got released? 50%. Let's say we're really going high. We only have 20 millimeters of mercury of oxygen because we're really using it up. Okay, 30% saturated. How much to release? 70. If this was a plateau, it would say, hey, that's all I'm releasing. The reason it's steep is we want this responsive to the needs of the tissue. Okay? If you need more oxygen, it releases more oxygen. That's why you want it shaped like this. Does that sort of make sense? It's the opposite of this. Here we wanted it to stay the same because its job was, let's pick it up as efficiently as we can, even if conditions aren't right. Here, we want this totally to be responsive to the needs. If we need more oxygen, it releases more oxygen. So we actually have it sort of in the steep phase. Okay? Again, I have it this way. If the cell is active, more is released to, again, meet the cellular need. Again, less oxygen means you need to deliver more. Again, it's delivering more. Those are the two phases, yes. Yeah, because the idea is, and we'll kind of do this again, and we'll actually do this, when you talk about high metabolism, we did this a little for the active hyperemia, that means you're using up your oxygen and building up CO2. So the higher metabolism you have, the concentration of oxygen keeps getting smaller and smaller and smaller. So high active, you have less and less and less oxygen, which means you want hemoglobin to deliver more and more oxygen. Does it do it? Yes. Okay, does everyone sort of see, again, there's other reasons of why it's shaped this way as far as chemistry goes, and I can talk about that offline, because for people that are really into sort of how this molecule works. But for me, I want to get it in sort of physiological significance of why it shaped this way works for us, is very efficient. And that's why you sort of go into these, again, the next step of this, and we're going to have to stop in a few minutes and not get to all of it. So that's why Wednesday's going to be. You want to utilize this extra time of no labs because we're going to cover a lot of stuff still in all those periods. We have 3 periods, basically we have 5 hours coming up because we're not going to get fully through this. But at this point, for the hemoglobin saturation curve, and then I'll introduce the next point that we'll start on. At this point, we have basically, the idea of what the axes are, and then the shape. So you want to start when you're practicing this, talk about this, and then that. This again, what's on here, it's the loading phase, because this is where it's loading up with oxygen, and it's pretty efficient. Almost becomes 100% saturated as it passes through the lungs. Pretty good. Okay, yes?
If 100 on the far right side of the graph is at the lungs, and then 40 is at the tissue, does the 40 to 0 mean as it's coming back to the heart or to the lungs?
It's meaning, no, it's meaning if, this is at the resting cell.
Uh-huh.
It's saying, this basically is, if the cell is more metabolically active, that tissue is gonna have less, and less,
Okay.
okay? And it's gonna deliver more, and more. So, when it gets past there, it's gonna depend on basically how much you get used up here. But overall, usually, for most tissues, it's going to come back to lungs still almost 60-70% saturated. It doesn't have to pick up that more. If basically if you're running away from a bear, you're going to be using up a lot more. It might only become 50% saturated as it gets up there. But of course, it's going to bump right up to 100 no matter what.
So from 40 back down to 0, that's all at the cell level.
Yeah,
That's
but
just a matter of
but
how
again,
much
that's where I
you're
don't like this that much because it's not going to be 0 unless you're dead, right? This is almost this is like a chemistry curve. We'll put that in a test tube and expose it to this, all these concentrations, and this way it looks. The physiological significance is basically about 40 to 20. So if you're really highly metabolic active, your tissues might only have 20, and you're giving up that much. You're rarely going to have anything lower than this unless things are really going, bad for you. That would be 0 seems like it'd be really bad. That's why you don't want to think from 40 to 0, but because again it's chemistry curve. But you could think of this range as being sort of resting up to metabolically active,
Okay.
and so that will be sort of that. Okay, so it's loading, but it's a plateau because or at least the advantage of it being a plateau is that less than normal oxygen concentrations in the lungs, we're still going to become fully saturated or almost fully saturated. That's pretty good. You go to the next one. The unloading or steep phase. We did this, we do this. Again, it's called the unloading because that is where we're unloading to the tissue. We're not keeping it up, just passing it by. We're taking some of that and delivering it to the tissues. That's why it's called the unloading phase. Again, reminding us that, at the kind of resting cell phase, 75% saturated means about 25% is being released. It's not releasing all of it. But as you go this direction, high metabolism, you have less oxygen, you need more, it is responsive. That's why it's steep. The more you need, the more it releases. Again, that's why saturation is a chemistry term, but if you think about releasing, again, if you're at this level, 50% saturated, that means it released about 50%. If you're at this level, 25% saturated, it released about 75%. So if you start thinking in those terms, I think it starts to have more significance than, unless you're a chemistry person, you can talk about saturation, that type of thing.
So for hypoxia, what would it look like? Because that would be, we need to know that.
We'll wait, yes, we'll wait. Because what we're going to do next time, because you'll have this all done by Wednesday, is talk about when these curves, we'll kind of put a better one, shifts to the right to the left. We're going to show you sort of the significance under these different conditions, which could be hypoxia, that idea. So we're going to do that, and we'll look at a couple of these things up here, pH, temperature. All that's going to relate to one thing, metabolism. I'm going to show you. So the next step will sort of follow as well. So try to come in Wednesday. Again, you want to do well in this test, forget your life. I hope you have forgotten your life, right? I mean, you live alone and you study, okay, and you're going to YouTube and listening to me 24/7. Try to come in doing as much as you can with respiratory and this, so that we can then move on and finish this and go to the kidney. And again, I'm staying late, okay? So I'll stay to 10 o'clock when we need it. We'll be able to go over, finish 19, and then stay and just practice for people that want to do it and go over it more and more and more. So, but we do have lab tonight for the people that didn't have it. So get ready for that. And it's not terribly long either overall. So again, I'm available tonight as well to help people go over it. You paid for me. Use me.
Do you have our lab quizzes? We did.
Yeah, I left it with Calamar too. I was like, we're on that.